Hello, welcome to our presentation. We have called Short and Easily Wide Area Monitoring, Protection and Control and Necessary for Future Monitoring and Operation, actually. So we have divided our presentation into two parts. First, I from the TSO part will say a little bit about our challenges and need for safe future operation, please. And then Geir will tell about how we can develop the system together with our external partners. So I'm Kjell Petter, working as a senior advisor in R&D Statnett. And Geir?
I'm Geir Borse. I work as the CTO for Unicus, an auticon company.
Yep. So actually this motivates us. Even if this happened in Spain, we have heard many times about it during this conference. It's motivates us. Can like this happen in Norway? And we are afraid it can. And one thing, this picture is actually taken from the NSOE report, and it's not so easy for operators to understand what's actually happening. You can see the voltage vectors pointing in several directions, but it's very hard to actually detect the problem. So actually this motivates us to work further on and make the information better to the operational. Please, next. So we come from Statnett, Norwegian transmission operator. We are owned by the government, National State of Ministry Energy, and we own and operate the transmission grid in Norway, and we operate it together with our Nordic partners in Sweden, Denmark, and Finland. Actually, we have three control rooms, two in Oslo and one up at north in Alta. And this is just some key takeaways from our grid. We are not so big, but big enough for Norway. We also have subsea cables to Netherlands, UK, Denmark, and Germany. We are approximately 190 substations and 600 employees, more or less. And we have also installed approximately 150 PMUs in our grid. Next, please. So this is also from our grid, and I said we have net exchange to Finland and Sweden, Denmark, UK, and Netherlands. So that means that we collaborate very closely with all our Nordic partners, but also have interlinks to the continent and the UK. And the production is mostly hydropower today, but wind and solar are increasing. And also there's a huge demand coming in, so the numbers there is quite now, but it's expected to rise. This is actually it's not special for Norway. We see that will be a lots of solar and wind coming in, and we need to tackle that in a secure operation in the near future. So it's not special for Norway, but we as operators need to handle this, and the grid operates in a completely new way. Also seen in Spain, where we have so much solar and wind coming into our grid, and our inertia will be less. Next, please. So actually, this is the case. Today, we can monitor the grid in seconds with the hydropower plants and much of inertia, but in the future, more will come from power electronics, and then we need to monitor the grid in microsecond level, even in nanosecond level. That means we need to tackle much more data in a high resolution, and also be able to detect the data quality and do anomaly detection on the data. So that's actually challenged the whole data infrastructure. Next, please. But also a time synchronization, because we shall compare data in a wide area monitoring system. We collect data, high resolution over a huge area in Norway is 700 kilometers approximately. So that means the time synchronization is also crucial, also transfer of data. So that also we need to handle to be sure of the data quality. But we did a research project called NEWEPS. We did that together with our neighbor Svenska Kraftnät, and that means actually to use the same user interface, also more or less the same system, to actually, so the operators in Sweden and Norway can actually collaborate much more and see the same alarm and the same user interface. We did all the simulation on sim model. We can take the next, I think. That means we also uses the 3D image, and we was actually able, if you use 3D image, you can show the grid in you can actually show more efficient how the oscillation is developed, and you can actually see the root cause of the oscillation. You can actually see it much better than only alarm. Next, please. And so we developed this together with also people from the gaming industry. That means to drill down in the system. Today you need to scroll down lots of different user interface, but to have only one operate in one interface, but be able to just move around and click around, or like you're doing in gaming, and the information will just pops up. We believe and was showing that the information was much more easier and better to get access for the operators. We also use the 3D. That means we are actually able to show the subgrid in the DSO side, the regional grid, how it's connected to the transmission grid. That means you can actually see better how things are connected to each other and the root cause and also collaborate better with the DSO. Yes, this was also one thing we developed in the NEWEPS with using impedance method. We can actually show the border from the instability area when it comes to voltage detection. So operator easily can show how large the margin is to moving into voltage instability grid only with. So the operator can actually choose more or less what's needed, how much margin he wants to have operating. And we also use the 3D image to detect islanding, because that's also have been one of our challenges. Of course, it's based on the PMU values, with showing different angles. Then we can easily show to the operator how the frequency divides in each island, and be able to easily detect islanding, and also be able to bring the grid together again. Yeah, that's please. And this was also the 3D was also using, you can see better the root cause of the oscillations. So I think just take the next one, please. Yes, and we was also showing that with more or less a very high level, so you can actually see the root cause on a higher level. Next, please. And you can also see which asset was actually oscillating to each other, with highlighting the line that was most affected by oscillation. So it could actually see where to actually to regulate, to actually bring it back to a secure state. And we was also developing what prediction actions, what should the operator actually do. In this case, it's shown as a delta regulation, so showing to the operator how much it need to do actions to bring it in back to a secure state. Next, please. And this was actually how we develop it. We develop it by everything is now, all the code is now on Python and Statnett GitLab. We was using a Kafka stream by PDC, and we was simulating PMU data, but also was able to import historical data, and all the microservices is now in Python on Statnett GitLab. Yeah, next. Yeah, and we also have made some nice videos on YouTube together with our research partner SINTEF Energy. So if somebody is interested to see how we actually was able to visualize the voltage stability, oscillations, TSO coordination, and also corrective actions, then of course you are free to look at the YouTube videos. Then you will tell about how we able to develop this further on together with our partners.
Thank you. Thank you for the chance both to speak and also present with you on the stage here. This is my first time at LFE, and it's also the first time of Unicus. So I'll take the chance to say a couple of sentences about us. We're an IT consultancy, but we're also a social enterprise, meaning that all the IT consultants hired by Unicus is on the autism spectrum. What we're cooperating with Statnett on is building a system for WAMPAC, but also a system that allows Statnett to test research hypotheses, to test implementation of open source software. When we started this cooperation, we looked at CERN and how they were able to use their open data platform to invite researchers from across the globe to cooperate on investigating their petabytes of data. And this is Statnett's version of the very same question, how to invite external researchers to investigate Statnett's confidential data, come up with answers to questions that we require expertise, world-class expertise in discovering the answers to. I'll go into detail with most of these, but what you'll see is that we've used open source software from as top to bottom as we were able to. When we investigated the CERN Open Data Platform, we came up with some requirements for Statnett's very own open research platform, and I'll go into detail in each of these. Now, grant external access. Without allowing external users access to our platform, there was no need for one, so this had to be resolved. Unfortunately, we had to use Entra, but all of Statnett's users already have an Entra ID, so this was easy enough for us to choose. We could then piggyback on a bit of their solutions for allowing external users to come on to their platform, and also to set a time limit for when these users should disappear as the consultant's contracts finished, etc. All the rest is open source. Open source and cloud agnostic is super important for Statnett for this project. We've only used open source software. This allows us to do our research. It allows us to make changes quickly. It allows us to distribute results made on this platform freely. And of course, the most important part, it allows us to have control over the functionality we need. I also said cloud agnostic. And again, we met with a little bit of problems here, as Statnett has approved exactly one cloud vendor, meaning that we have built a platform on top of Azure, but we've tried as hard as can be to be ready for the second, Statnett approves a second vendor. So when GCP or AWS or a sovereign cloud somewhere in Europe comes online and is approved by Statnett, I would very much like to be the very first Statnett project on board that platform to prove that we've built a cloud agnostic project that can really be used. We are as exit ready as we can be. So the second Kjell approves that we can move to a different cloud, we're ready. So I said cloud, we're obviously then scalable. We support dynamic compute. We have set up a number of different pods already with CPU memory. We have planned GPU support as well to train our own LLMs. Each user, of course, gets their own pod, meaning that we have a uniform OS for each pod, meaning that there is no chance of a researcher destroying or interfering with the results of any other unless they share data. One of the very most central features for Statnett as well was to be able to show which resources had been used by whom, by which project. So of course we log every user and see how much each and every one is using at any one time, and can of course summarize that over day, month, year, whatever. Now, storing large data sets is of course exceptionally central. We want to be able to know that Statnett's confidential data remain confidential and remain only with the researchers that we've granted access to the different research projects. So our data is encrypted at rest and transit, and of course also in use. I've seen other use the Ceph file system. We're based on an Azure platform with guardrails, meaning that somebody else has also set up security fences for us. But we've tried as much as possible to ignore that we have these fences and make sure that we've built as secure a system as we are able to, knowing that next time we rebuild our system, it could be on AWS, it could be on GCP, it could be on Oracle Cloud. And when all of these features have been combined, we still don't really have a system until we are able to support any researcher with any research tool that they can reasonably ask for. We've set up a default system, a default version of Python, a default version of R, but any researcher can ask us for any other library, any other version, or they could just install it themselves. We offer a support for white sourcing it with Statnett Artifactory. But if you have a homegrown one that you want to use, sure, load it up, no problem. We, of course, support code versioning, GitHub, GitLab. If you really want to use Bitbucket, you're welcome to do so. We have a project online and running at the moment. And of course, the very first thing they asked us for was, ooh, great, we could use your platform. But we have lots of proprietary software. Can you please install it all for us so we can use our software? And of course, they wanted to use OpenAI APIs as well. So we are as open source as we can be within the limits of serving different research projects. When they come say, we want to use proprietary software, sure. Cooperation is the name of the game. Now, last time I presented the platform that we've built, I really couldn't answer that we've served each and every requirement. This time I can, because we have a reactive and dynamic visualization that is open to the web for demoing. Unfortunately, it is exactly the proprietary software that I just complained about, and I really don't want to do commercial here for a proprietary vendor. So I am really looking forward to be able to come back next year and show off how we can do open source reactive and dynamic visualizations on our platform. So we have built a system ready to support Kjell-Petter's WAMPAC solution. And I really hope that we can show some of that for next year as well. Thank you. Any questions?
Not DNV anymore. Kjell-Petter, when did you start your project with the PMUs? And then the question comes after to Geir, when did you start building the platform?
Yeah, thank you. The project was actually established as a Nordic project, I believe. It was funded by the Norwegian Research Council and the Swedish Energy, and we was really starting up this project for 4 years ago. And we have now ended the project, and we will hand it over to Geir. So we have done this work on 4 years. Perfect.
And we hope to be able to build, we started this platform a year ago, and we hope that when we see each other again in a year, if not sooner, we'll have a WAMPAC project up and running for you as well.
Good, but 150 PMUs putting into the field, that needs some planning and some... You have 100, you said you have 150 deployed. Netherlands want to have 150 deployed, but I think we have 6 now.
Thank you. That was a very good question, and it also shows that we, from a TSO side, need to speed up to actually be able to avoid some blackouts in the future. We have installed 150 PMUs in our grid, and that's they are still used in the back office, or systems in back office, but moving the PMU values into the control center. That means a completely another story, because there are reliability on the PMU and the databases supporting the PMUs. It's good enough for the back office, but it's not good enough for the control center.
Anyone else? Thank you.
Thank you.